It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming You a Nice Coffee.
Okay, so the final video I'm going to be doing around the collision theory is going to just focus on the use of catalysts. Okay, so remember collision theory, in order for particles to react, they must collide with the correct orientation and the minimum energy required. Okay, now what catalysts do are really, really great. Okay, they will basically improve a rate of reaction in almost every way. So catalysts provide an alternative reaction pathway with a lower activation energy. So not only do they impact on the activation energy by lowering it, okay, but this alternate reaction pathway normally involves lining the particles up with the correct orientation as well. Okay, so we're going to be hitting basically all this energy of particles and the orientation of the particles here. We're not going to be impacting upon the frequency of collisions, right, but we will be impacting upon the energy of the particles and the orientation. I'll explain that. So let's start off by talking about here providing alternative reaction pathway. Okay, so what I'm going to do is I'm going to use a energy profile graph, okay, to talk about the effect that a catalyst can have. Okay, so what I'm going to do is I'm going to use a energy profile graph for an exothermic reaction to explain the effect or how this alternate reaction pathway occurs. So normally up here in an exothermic we have our reactants which have a higher energy than our products. So here's our normal energy profile graph. Okay, what we do when we introduce a catalyst, okay, is instead of our normal activation energy being this distance here between the reactants and the top of our peak, okay, what a catalyst does is it lowers the activation energy like that. So it doesn't have any impact upon the energy of the reactants or the energy of the products or the enthalpy of the reaction. All it does is reduces our activation. So this is called EA dash, all right, that's our new activation energy, and that's with a catalyst. Okay, so we have a lower activation energy, which means the reaction, all right, will be able to occur faster because they'll have more particles with that energy greater than or equal to the activation energy. Okay, you can also show this through an energy distribution graph. So if we bring an energy distribution graph down here, okay, and we have our normal bell curve distribution, okay, if this is the normal activation energy, we know that only these particles will have energy greater than or equal to the activation energy. What we do when we bring in a catalyst is we lower the activation energy. So here's the new activation energy in here, which means you have a lot more particles, all of these, which have energy greater than or equal to the activation energy. So what that means overall, okay, is this. Okay, and I'll choose a nice color to show this. So we've got more particles having energy greater than or equal to the activation energy. Okay, so that's key to think about. So we're not changing the frequency of the collisions, okay, but what we are doing is saying that when they do collide, it's more likely that they've got the energy higher than or greater than the activation energy. Okay, you bring into that the fact with that the alternate pathway quite often, all right, provides the correct orientation. Then overall, what you're going to be having is that, now I said remember it doesn't impact on the frequency of collisions. What it does though is it means that the frequency of successful collisions, those that have the correct orientation and the minimum energy to react, so the frequency of successful collisions per unit time, because that's key. All right, so the frequency of successful collisions per unit time increases. Okay, so because the frequency of our successful collisions per unit time increases, a catalyst, due to the fact that it provides an alternative reaction pathway with a lower activation energy, means that it will increase the rate of our reaction. So there's lots of examples of where this occurs naturally. Photosynthesis is a great example where it uses light, okay, it's come down, and that helps to catalyze the reaction of carbon dioxide and water into glucose, okay. Without the presence of sunlight, the reaction is incredibly slow. That's why if you put a plant inside a dark room, it won't grow, and normally it'll die because it can't photosynthesize. You don't have that catalyst for the reaction, it just doesn't produce that glucose fast enough, which is the building block for it. Okay, another example is enzymes, so using yeast for making bread rise, for example. If you try to bake bread and you don't add the yeast catalyst in, you won't get the reaction occurring. Okay, so it's really important that you use a catalyst, okay, if you want to speed up a reaction that's quite slow. And the final thing that I want to leave you about, which is really, really beneficial for catalysts, okay, is that you only need a trace amount. What we mean by trace amount is that you only need a really small amount. They're not used up in the reaction, okay? Basically what they do is they grab one particle, they grab another particle, they bring them together to react, and then they release them. Then they grab another and another, bring it together, react and release, okay? So you can use just one small thing to do a massive number of reactions, and you can get it back at the end, which is really, really beneficial. Okay, that's why catalytic converters in a car, which convert carbon monoxide and nitrogen monoxide into carbon dioxide and nitrogen gas, you can just have your catalytic converter sitting in your car, okay, and that will continue to convert those gases over and over and over, okay? You don't need to replenish it or replace it, all right, because it will just keep doing it and the catalyst doesn't get used up, all right? So, hopefully this has been helpful. Really encourage you to go back over all the videos, in particular focus on the big three. So first one I looked at was temperature, then look at concentration, then look at catalysts and the effect that all of those have upon the rate of a reaction. Make sure you can explain it in terms of the collision theory. So reference energy of particles, orientation of the particles and the frequency of collisions, okay? And then always come back to what impact it has upon the frequency of successful collisions per unit time, and you can use that to explain your rate. Okay, hopefully this has been helpful. See you later. Thanks, guys.